All right, everybody, welcome back to EM378SI Online. We'll start with a couple announcements here. Regular WebEx times that we're going to have for just a few more weeks here because the semester is about to probably wrap up sooner than we think. So Monday, Tuesday, Thursday, 665. So catch me if you want to ask questions or want to see more problems worked out, anything like that. And also, we have an exam review. Hopefully, you guys saw my SI announcement from earlier today, but if not, here it is now. We're going to have WebEx, and that's going to be at, let me remember, 2 p.m. Iowa time on Sunday, the 12th. So that's where we're going to be doing general questions and also some multiple choice and fill in the blank. And then I'll be posting some more YouTube videos, which it will be problems solved, sorry. And those will be based on mock exam that I'll post on the SI website. So a mock exam is going to go up tomorrow, hopefully. I'm planning on getting around to it then. And then I'll answer. I won't post solutions. Solutions will be done for multiple choice in the WebEx, and then for the problems, I'll finish those on YouTube. Or maybe I'll do all of it on YouTube. We'll figure it out when we get there. But if you got questions, if you want to see answers to problems and that sort of thing, tune in this weekend for exam review. All right, and now we'll get started on this problem. This one's a little bit different from what we've seen before, and you'll see why in a bit. All right, so we got water pumped between two large open reservoirs through 1.5 kilometers of smooth pipe. Remember, that does not mean that friction equals 0, just means that epsilon over d is 0. That comes around later. All right, and the water surfaces in the two reservoirs are at the same elevation. When the pump adds 20 kilowatts to the water, the flow rate is 1 meter cubed per second. If minor losses are negligible, determine the pipe and diameter. So minor losses just means delta KL is 0. All right, let's get into it. So we have our 2 points here, 1 and 2, and usually that means Bernoulli. So we're just going to quick write a couple things out. Pressure, volume, elevation. So the convenient thing about this problem is that the pressure at 1 and 2 is 0 because it's open to the atmosphere. The velocity at 1 and 2 is also 0 because it's a large tank, and the elevations are equal, so we'll just call that 0. So what happens to our Bernoulli equation, which is originally looking like this, just becomes, which is convenient for us, right? But notice that, so we have our loss on this side and we have our shaft head on this side. And what we'll want to remember is that our HS, so I'll rewrite this way actually. So HS is W dot over gamma Q. Our W dot, or our power of the pump that we have, is given as 20 kilowatts. And then we're working with water, so our gamma is 10.8 times 10 to the third. And our Q is just 1. So we have our HS is 2.04 meters. Remember, this is in terms of head, so our all the values that we're going to get, all of our terms are going to be lengths. So we have 2.04. And then the other thing that we need to solve for is, so then if we can get HL into terms of our diameter. So we know HL is friction L over D B squared over 2G. And we want to get all of this in terms of our diameter, or at least what we don't know, right? We know the length of it, that's 1.5 kilometers. Diameter is what we're looking for. Velocity we can get in terms of diameter using our continuity equation, and then friction factor, that's going to be something different. You'll see in a bit. So velocity, right, Q over A, that's just it's just 1 over pi over 4 times our diameter squared, which is 273 diameter squared. So now we have that HL is friction 1.5 times 10 to the third over D times V squared over 2G. So that V squared is 1.273 over D squared, 2 times 9.8. And what happens with this HL is that we get, that's 123.9 friction factor over D to the fifth. So now all we need is to figure out what this F is, and then we're in smooth sailing, right? So let's see. Let's get F into terms of D, because we're going to need to solve that later. All right. So we know HS equals HL. So 123.9 friction factor D to the fifth is equal to 2.04. And so D is 2.27 times F to the 1/5. All right, but now here's the question. How do we get our friction factor? We do that with, remember, we determine what the Reynolds number is, and then whether it's laminar or turbulent is, we move forward from there. But in this case, our Reynolds number involves something that we still don't know, which is our diameter, right? So rho v d over mu, 999 times 1.273 over d squared times our diameter over 1.12 times 10 to the negative third, which is just 1.14 times 10 to the sixth over our diameter, which is not a number that we can work with. And so to move forward from here, what you can do is you can use trial and error method, where you plug in an F value that you think works and then check with the Moody chart based on that. I think Dr. Schaefer went through an example with that, so I'll just do a different version with you guys. Because I never personally use the trial and error method. I always use the Colebrook or Holland equation, because we have a relationship between D and F, and we also know, so the Colebrook equation is 1 over square root of our friction factor, negative 2.0 times the log of epsilon over D over 3.7 plus 2.51 over the square root, over the Reynolds number times the square root of our friction factor. Kind of a messy equation, but that's fine, because we know F in terms of D, and we know our Reynolds number in terms of D. So what we can do is we can plug all of that mess in to figure out an equation in terms of D, and then plug that into our calculator and walk away. So we would get, if we plug in this equation and this relationship, so 1 and 2 So we'll put 1 and 2 into this, and we get 1 over 0.0165 times d to the 5th to 1/2, so that's your left-hand side, negative 2.0 times the log of, we know epsilon over d, because a smooth pipe is 0, but that doesn't mean our friction factor is 0. So we have 0 for this term, and then plus 2.51 times d over Reynolds number. Well, I flipped the Reynolds number because it's in the denominator, so that's where this d came from. And then we have the 1.14 times 10 to the 6th in the denominator, multiplied by our friction factor over here, which is 0.0165 d to the 5th to the 1/2. Kind of a mess, but what you'll get is that d is equal to 0.926. Now, if you don't like how this looks and it's kind of a mess for you, what you can do is you can do a little bit of substitution where you say that like x is equal to 1 over the friction factor, and then you can say x is equal to negative 2.0 times the log of this thing, 2.51 times d over 1.14 times 10 to the 6th times what would be x to the 1/2. But in the end, you'll get the same thing. So if you have a calculator like a TI Inspire or what's that other TI one? There's a bunch of equation solvers. Even I think a TI-84 would do this for you. It would just kind of be a pain. So it'd be worth your time to figure out how to solve equations on your calculator if you haven't done so already. Alrighty. So that's how this problem works. You'll get a diameter of just under 1 meter, which means you'd probably want to go with like a 1 meter diameter pipe if this is like a design problem, but that's neither here nor there. The answer you get 0.926. So I'll say it one more time, and then that'll be the video for today. WebEx meetings, regular weekly, and this exam review. So WebEx, 2 p.m. Iowa time Sunday. That's where I'll be answering general questions, going through the multiple choice and fill in the blank that I'm going to post tomorrow. And then on YouTube, I'm going to post problem solved, everything like that. So stay tuned for that this weekend. And then, yeah, like I said, these two are going to be based on the mock exam that I'm hopefully posting on the SI website tomorrow. Hopefully by the afternoon, but kind of depends on what my other classes look like. All right. Have a good day, everybody. I will see you in the exam review.